Thank you very much, and great seeing you here. And thank you, the organizers, for having me here in this vibrant and interactive meeting. Now, what I'm going to tell you today falls under the title Quantum Cooling, which is a very vibrant and intensive emerging direction of research. And specifically, I will consider dilute quantum cooling. Of course, I will need to explain it, and a few niches that emerge from there. So this talk is based on two works, one published. This is the team. Kirillo participates in this meeting, but he's not here. And the second, still unpublished work in collaboration with my Chinese colleague, Xuan Wang. So this is my plan for today, and it's quite ambitious. I will remind you what quantum steering is. Then I will spend some time on dilute cooling, and then I will discuss what happens when a system cannot be cooled or cannot be fully cooled. And since this is quite a greedy plan, I will be able only to give you a sketchy flavor of each of these items. So we start with steering. So steering is all about performing measurements, following some protocol of measurements, and pushing a quantum system into a desired, pre-designated state. And I will, of course, focus here on many-body, in the case of a many-body state. So here are the principles of quantum steering. I have a system with its degrees of freedom, and I have a detectors. You may think of the detectors as the qubits, but it's not necessarily so. Now, before each infinitesimal step of my steering, I initiate the qubit in a given state. This state is predetermined and is independent of the running state of the system. So at a certain time, I switch on coupling between the system detector. I switch on system detector Hamiltonian. Let the universe of the system detector evolve in a unitary manner. And what I have is the following. The state of the system and detector at time t plus delta t at the end of this interval, this is the density matrix, is given by the state of the two at time t, at the beginning of this interval. At the beginning of this interval, mind you, we have the running state of the system, rho sub s at time t, times the independently prepared detector, the initialized detector. And we let the two evolve with the system detector, following the system detector evolution operator. So the question is, once we are done with this evolution and we decouple the detector from the system, what next? And we have several options. The simplest option would be to take the detector, not even look at the readout, and just throw it to the trash bin and take a new detector from the shelf, reinitialize it, and repeat the procedure. So mathematically, this amounts to tracing out over all the possible readouts of the detector, and I will refer to it, for obvious reasons, as blind steering. So blind steering is an instance of a more general class of steering protocols, which I will call passive steering. In passive steering, the steps of the steering protocols are predetermined and do not depend on the readout of the detector or on the running state of the system. So such a class of steering protocols is one out of three paradigmatic classes, which are listed here. We have post-selective steering, and we have a very clever active feedback steering. Today, I will not touch these guys. I will focus on the stupid protocol, the blind steering or passive steering. I believe that the first work that I mentioned that was the work we did in collaboration with Stita Roy, who also is not here. So let's see how this works in a paradigmatic example. So I consider an Affleck-Kennedy-Lieb-Tasaki, AKLT, chain of spin 1 degrees of freedom. And in order to avoid complications of the generate many-body states, which is a very interesting problem, can be dealt with, and gives very interesting results, but for now I want to avoid it, I will consider a chain with periodic boundary conditions where I have only a single non-degenerate ground state, and this is the Hamiltonian of the system. Sum over all spins in the chain from 1 to n. L is the index of the spin site. Alternatively, and more transparently, the Hamiltonian can be written in this form. I have a sum over links, the link comprising a spin on site L and the spin on site L plus 1. These are projectors. So if I have two spins, spin 1, the total angular momentum, the total spin, can be either 0 or 1 or 2. And this takes two neighboring spins and project them onto the sector of total spin equals 2. Since each of these terms in the sum is non-negative, the ground state of the AKLT Hamiltonian must have 0 weight in the total pair of spin, total pair spin equals 2. It can have only weights in the sector 1 and the sector 0. So that's the definition, or that's the construction of the AKLT ground state. So in principle, my steering should look like that. I mean, I have this chain, and I have a set of detectors, and here are three requirements which are very reasonable and make it interesting, non-trivial, and also, in principle, experimentally doable. So the first requirement is locality. I would like each detector to be coupled to a small segment of the chain, and the size of this segment should not scale up when I scale up the size of the system. Second, I want the system detector Hamiltonian not to change, at least the complexity of this Hamiltonian, not to increase when the length of my chain increases. And thirdly, I would like to accomplish my steering towards the ground state of the AKLT with a number of detectors which scales with the size of the system not faster than extensively. Scales, the number should scale proportional to n. Even then, having all these detectors and reinitializing them is quite an expensive resource, and we'll need to deal with it a little bit later. But these are the three requirements. And here is how we go about it. So this is my chain with periodic boundary conditions, and this is a link. And what I want to do is apply a measurement protocol, apply a system detector Hamiltonian that will take components from the sector total spin equals 2 and move them to either the sector total spin equals 1 or total spin equals 0. Now, how to do this is not uniquely determined. I have some freedom in how to do that. For example, look at this operator, which represents the operator of the system detector coupling, or alternatively, if we go to the continuum time limit, it represents a jump operator in my Lindbladian dynamics. So this operator will take a component from the sector total spin equals 2, SZ equals 1, and move it to total spin equals 1, SZ equals 0. And since in my undesired space, total spin equals 2, I have 5 independent directions. This is a 5-dimensional Hilbert space. I need 5 independent detectors or 5 independent jump operators in the language of Lindbladian, or 5 independent system detector Hamiltonians on this link. But once I define these operators, I can achieve the goal. And this is how numerical runs look like. Here I plot the distance between the running state of the system, represented by rho system at time t, and the target state, which is the ground state of the AKLT chain. I can define this distance using the Frobenius norm or the trace norm, but either way, you can see that this distance decreases exponentially with time, or with the number of repeated infinitesimal steering steps. All right, so this is what I wanted to tell you about steering. So steering is about pushing the system towards a pre-designated state. If this state turns out to be the ground state of a certain Hamiltonian, then we can talk about cooling. And indeed, if we have a system which is governed by some Hamiltonian H0, and we have all these steering detectors, and we manage to bring it to the ground state, we can claim that we were successful in our ambition. But as I mentioned, we need a large number of detectors, which scales like the number of degrees of freedom of the system, and the scaling can involve also a number, like in our case, it was 5 times n number of detectors. Can we be more economical? And by more economical, I mean, can we consider the same system with the same Hamiltonian, but actually do the steering only on one link? If we are successful in that, I will call this dilute steering, because we took only a small segment, or alternatively few small segments of the system, and do this work on those segments. So before I try to dive deeper into that, let's apply the same protocol, but only for one link, in the case of AKLT, and see what happens. So here, this is the time or the number of steps. Gamma, to remind you, is the strength of the coupling of the detector to the link, or the coupling constant of the Lindbladian. Here, this is the logarithm of the distance to the AKLT asymptotic ground state. Psi sub t is the running state, AKLT is the ground state of AKLT. And you can see that for different lengths of chains, this dependence is exponential. So seems to work, at least in this example. We had a couple of other examples. For example, we did it for the Majumdar-Ghosh model. It's a model of a spin half chain where we take three neighboring spins on sites I+1, I+2, and project them onto a total spin equals three halves. We did it there, and again, the convergence of this dilute steering towards the ground state seems to be exponential. Yes?
So most cases, the feeling is unique, right?
It's the ground state.
So then the gap is different here.
The gap is different.
But you don't have analytical bounds in the gap, it's numerics. Right?
This is what I'm going to do in the next couple of slides. Okay, thanks for the question. So let's try to see whether we can develop some more analytic understanding of what's going on here. And in order to do why this works at all, when the jump operators of this Lindbladian are local. And let me start with a definition, which was exactly raised by you. I have a Liouvillean dynamics, which is a linear equation in rho in the density matrix. So I can solve it, and I have a spectrum of eigenvalues. At least one, but possibly more than one, of these eigenvalues must be zero. And this represents the stationary asymptotic states of this Liouvillean evolution. If I have more than one eigenvalue which is zero, I have a stationary manifold. If I have only one, I have one asymptotic state. So now I go to I denote by delta the gap of this spectrum, which is the magnitude of the real part of the eigenvalue closest to zero. And this delta represents the slowest rate of decay towards this ground state. So having done so, I next consider a particular link, which is the cooled link, and I define the Hilbert space of this link, the link I+1. And I divide this Hilbert space into two sectors. There is the cold sector and the hot sector. The cold sector will be the support of the target state, rho plus is the target state, on this link. In other words, I have the target state, I project it onto this particular link. That would be my cold subspace on this link. Everything else, which is the perpendicular part of this Hilbert space, will be called the hot subspace, which I also call the kernel of the ground state on this link, I+1. So the aim, the target here, is to have a protocol, at least the immediate target, maybe not the eventual target, but the immediate target will be to take all components from the hot subspace and move them to the cold subspace on this link. So the key question, as you pointed out, is to have some estimate of this gap, of the rate at which I can achieve this. Instead, we have an expression for what we call delta estimate, which is a bound from above of the real delta. But if gamma, my coupling constant that appears, my coupling of the detector to the system, or the coupling constant that appears in the Lindbladian, is sufficiently small, and if you ask me, I can tell you what sufficiently small is, then the estimated delta turns out to be pretty close to the actual delta. So this is the answer for the estimated delta. It's 1/2 times Q times gamma. Gamma is the coupling constant. Q is obtained this way. I go over all excited states of the big system, all the bound states of the big system, and I project the state onto the hot subspace of the link, the cooled link. So I calculate these matrix elements, and I go to the smallest one. Intuitively, I go to the excited state, which has the smallest overlap with the Hilbert space on my particular cooled link. So I take this Q, and Q times gamma is my estimate of the rate. So in the case of the IKLT chain, I perform the cooling only on this link, and on this link, I would like to take the hot subspace, which is the sector 2, and move all components to the cold sector, which is the sector 1 and the sector 0. And as you already know, even with the dilute cooling, I need to have 5 different operators, or 5 different detectors, or 5 different jump operators acting on this cooled link in order to be able to treat all independent factors of this hot space. And this is the results. So first, the bad news. The bad news is that delta, my rate of cooling, seems to decrease with the size, with the magnitude of the chain. Interestingly, there is an odd-even effect. The blue refer to an even number of sites, the red to the odd number of sites. And the fact that delta decreases is not surprising. I'm cooling only in one place, and if my system is huge, of course I will need to increase more, to increase my effort, or to be more patient before I manage to complete the job. The good news here is that it turns out that the scaling of delta with the size of the system is not exponential, it's power law, and the power law differs between whether I have an even or an odd number. So all this seems to work, and of course, if we have a huge system, I can put not one, but several cooling centers to make my job easier. But I don't need to have the number of cooling centers extensive with the size of the system. That's the message.
Is there any simple explanation why this difference in the exponent for odd and even?
The question was why I have this odd-even effect. And this depends on non-commutativity. So imagine that I have my chain. What I do to this link in terms of the detector system operator does not commute with this one. So in some sense, if I run over, let me now go away from my dilute cooling. Let me have a full-fledged cooling. If I do something here, I will spoil a little bit what I managed to do here. So now the question is how much I spoil. If I have this one, this chain, or if I have this chain, the number of spoiling events will be different because this one will spoil both this one and this one. This one will spoil only one. So it's sort of a boundary condition effect. All right, so this seems to be fairly understood and okay, but then there is a red light blinking. And the way we encountered this big warning was when we did all this for chains of 6, 7, 8, 9 till 12 or till 15 in the case of Majumbar Ghosh. And then we decided to test it for very small systems, for very small chains, namely chain of 3 and chain of 4. And in that case, it turned out, first miraculously, that we cannot accomplish full cooling to the ground state. There were always some components left over, which were beyond the ground state. And the reason for that turned out that there are excited states of the entire system that have no overlap, no presence on the link we cool. So that was found accidentally for this system, but it can happen in general. So the question is, what can one do to overcome that? And the answer is that I add a kernelizer to this problem, or in other words, in the AKLT, I add to the original Hamiltonian an auxiliary Hamiltonian, which I call H additional. It's a Hamiltonian. It's not a jump operator, it's not Hamiltonian, it's a Hamiltonian. And I want this this Hamiltonian to change, to modify my excited, my states of the excited spectrum, but not touch the ground state. So here is a necessary condition for the success of my dilute cooling. First of all, this is obvious, cooling on a given link, I+1, is possible if the local hot subspace is not empty. Secondly, if I consider if I do that, and at some point I stop, I manage to get rid of all components of my local hot space, but still there are some global components that are left elsewhere. So I need to add a kernelizer, and the cooling is possible if there should be no state other than the target state that is invariant to both the measurement and all coherent interactions coming from this kernelizer. So if I don't, after adding the kernelizer, I am not left with an excited state which doesn't touch my cooled area and is not affected by the kernelizer. If this does not happen, then I'm successful. So, so these are the two messages here. And I now want to jump to ask the question, what happens if I cannot cool, even not in a dilute way? And before I raise the question and try to answer, I need to invoke the notion of frustrated Hamiltonians. So I apologize for using the word frustration, which is used in different contexts, classical statistical mechanics. Here it assumes very, very definite meaning. And you may protest that I use this language, but it's used there. So I give you a Hamiltonian, and I'm asking, can I use passive, stupid steering in order to steer towards the ground state of this Hamiltonian? So what I do, I define another Hamiltonian, which I call a parent Hamiltonian. The parent Hamiltonian in some cases may be identical to my Hamiltonian, but can be different. But what I require for my parent Hamiltonian is that this is a sum of local Hamiltonians. So each of these terms here applies to a segment of the system. So the question is the following. I give you the ground state of the system. If this ground state is simultaneously the ground state of all local Hamiltonians, the system is not frustrated. Now, mind you, if the ground state is simultaneously the ground state of all these local Hamiltonians, it doesn't mean that these local Hamiltonians commute. It's only the ground state. These guys may not commute. So if I have frustration-free Hamiltonian, it is steerable. This is the case of AKLT, for example. Otherwise, it's not steerable. So let's assume that you give me a Hamiltonian, which is not steerable, not passively, not stupidly steerable. What can I do? And the answer is that I cannot get what I want, steer all the way to the ground state, but I can still cool the system pretty well. And I invoke the notion of a surrogate state. Surrogate state is the state in Hilbert space which is closest to my target state, which is not steerable, but is still steerable. I'm telling you now a story, but all this can be quantified in equations. So if this is my Hilbert space, and this is the unsteerable, and this is my state here, I will take a state here, which is steerable. This is steerable. Take a state here, which is closest to here, and we'll steer towards that. Now the question, what does it mean closest to that? So I can define the distance to my unsteerable state using three different conceptual measures. One is to use the state. I measure how close the state, the surrogate state, is to the unstable state, and I can measure this by doing the fidelity. This is the surrogate state. This is the unstable target state. I can use the Frobenius norm. I can use the trace norm. Alternatively, I can measure the distance in energy. I take the surrogate state, I compute the expectation value of its energy using the original Hamiltonian. And now I measure the distance between the energy of the surrogate state and the true energy of the ground state. And I normalize it by it's very convenient to normalize it by the gap of the true system. And the third option is to do the following. I do my steering on the unsteerable state. I'm really stupid. I try to steer my state to the unsteerable state, and I do it for a very long time. Eventually, I cannot get any closer. So what I'll get components in the true ground state, but first excited state, second excited state, and so on. And I force this distribution to be a Gibbs distribution. And then I can define some effective temperature. And I can define how low in temperature I can do. If I were able to steer, that this temperature would be 0. So I can, these are global distances. I can do better using local distances, but I will not have time to go into that. So here is an example. Unsteerable state, SYK chain of Dirac fermions, different sizes of chains, and each histogram, each color is for different size of chain, and these are different runs. Asymptotic state of different runs, you see that they are shifted from 0, and the bound that we find analytically for the lowest, in this case, lowest temperature is somewhere here. So there is for these unsteerable states, there is a glass floor, lowest energy or lowest temperature, below which I cannot make it. And here are a few other models that we played with. So to conclude, I talked about states that can be cooled. I classified the Hilbert space into frustrated and non-frustrated, but the interesting or exciting news is that the structure of the Hilbert space is more complicated. It's not only two sectors, steerable and unsteerable. There is a frustration-free steerable. There is non-frustration-free, non-steerable, but there are also non-frustration-free, steadily steerable, and non-frustration-free, jittery steerable. There is a whole zoo here, and I will be able to discuss it at some other time. And these are my final comments. So the first message is that if we encounter states which are not subject to passive steering, for example, a GHZ state or W state, then clearly they cannot be subject to a dilute cooling. We found out that the dilute cooling is slowed down power law with N. And there are two questions out of many that I would like to raise here. First, imagine that I don't have a uniform chain or uniform array, but I have a very random landscape in Hilbert space. So I try to cool here, and there may be states that are trapped elsewhere in some valleys in Hilbert space. So do I have the notion of such trapping, glassy trapping, in this context of cooling? And the other one, the other question, and we have partial answers to that. If I go beyond my stupid protocol, I decide to look for active steering where I use my brain to decide what to do next based on my history, I'm a bit more intelligent than the stupid passive guy. Can I overcome these difficulties? And with this, I would like to thank you very much.
Thank you, Gefen, for a very nice and interesting talk. So we will have time for a couple of questions. Anybody with questions?
Yeah, maybe a little bit off, not directly related to your talk, but could you also decide, let's say you don't know whether a Hamiltonian is frustration-free or not, which is actually a question that sometimes comes up in complexity theory. You say, is there a state that satisfies all the local terms?
So, sorry, the question is whether, how do I find out whether
Right.
Hamiltonian is frustration-free or not?
Yeah, and so the question is whether such an approach could be used to determine this, maybe as a heuristic. I don't know if you have any thoughts on this.
So thanks for the question. I don't know of any proof to that. I don't know of any mathematical protocol to determine that, but I have some indicators that I suspect are indicators to whether it is or it is not. For example, I calculate, I take your system, your beloved ground state, and I calculate the entanglement entropy. If the entanglement entropy does not satisfy area law, I suspect it is not passively steerable. But I'm now, what I say is based on my experience and I'm speculating.
Yeah, I mean, if the terms are commuting, then I think the ground states should satisfy an area law, but that's a known thing.
If I what?
If the terms in Hamiltonian are commuting, which is different from frustration-free or not, then I know that the ground state should satisfy an area law. That has been proved, but okay, but you're saying something.
Okay.
Any more questions?
Hello, yeah. So could we steer to some excited state or some mid-spectrum state like this?
Can you repeat the question?
Could we like design something to steer to some other state, like not the ground state, some excited state or some mid-spectrum
Okay,
state?
so the question is whether I can use my protocol to steer not necessarily to the ground state. So in that case, I should not use the word cooling because I don't have any energy scale, but yes, of course. I mean, the whole thing of steering is the ability to engineer a state even when I don't have an underlying H0 in the problem. So if I don't have H0 in the problem, of course I don't have the notion of ground state is gone.
Okay, so I guess we should thank the speaker once again, and